Alright, you'll be able to distinguish between the atomic number, mass of an atom, and average atomic mass, and describe the structure of an atom and draw a simple atomic model for an atom. You'll also be able to extract information from the periodic table related to atomic structure and atomic mass. The atomic number of an element is the same as the number of protons in the nucleus and of that of an element. From the definition here we can see that the number of protons gives us the atomic number, and the periodic table is arranged by in order of their atomic number, the atomic number. So you've got hydrogen 1, helium 2, those are based on the atomic numbers. Number of protons is also equal to the number of electrons if the element is neutral. So how do we write this out and use some symbols to represent this? Here we have the X, which represents the chemical symbol, the Z that represents the atomic number, and the A that represents the mass number. So atoms, these are the basic unit of an element that can be enter into a chemical combination. There are diatomic elements, and there are also what are called polyatomic elements. From the prefixes here you can see di and poly, di meaning two, poly meaning many. Now the funny thing is, you go, wait, two atom elements, that means they contain two of the same element in their simplest form. And then polyatomic would contain more atoms in their simplest form. To remember the diatomics, all you have to do is remember the 7 at 7. So you look on the periodic table and you look up number 7, which is nitrogen here. The 7 at 7 are the 7 chemicals around the nitrogen. So let's look here, highlight this here. They're the 7 chemicals: nitrogen, oxygen, fluorine. Those are 3 of the 7. And then you go down: chlorine, bromine, and iodine. So that's 1, 2, 3, 4, 5, 6. So nitrogen, oxygen, and then the fluorine, chlorine, bromine, and iodine. And the 7th one, at 7, is hydrogen. These are all diatomic, so hydrogen is H2, nitrogen is N2, oxygen is O2, fluorine is F2, and so on and so forth. If you look on the periodic table here, the periodic table is arranged by groups. This is called a periodic property. As you can see, it looks kind of like a keyboard, 1, 2, 3, 4. The patterns repeat. So this here, BE, is going to have properties similar to NG. And then NE is going to have properties similar to HE and AR, for example. The elements are grouped by their chemical properties. So we've got lithium, sodium, and potassium, which we saw the demonstration for. They're all here in the same group. Period is represented by the row across. Again, these do not have the same chemical properties in a period. Groups do have the same chemical properties. Periods have some other things that are in common. So on the periodic table, the periods go in numeric order: 1, 2, 3, 4, 5, 6, 7. And then the groups go across the periodic table. On the top, 1 through 18, and that's how the international community numbers the groups on the periodic table. In the United States, it's 1A, 2A, then 13 is 3A, 14 is 4A, and so on, as you can see here. On the periodic table, there's a separation point between the metals and nonmetals. This is between boron and aluminum. Metals and nonmetals. Hydrogen is also a nonmetal, and then in the middle area there are the metalloids, who can act like metals or nonmetals. The families, which are also called groups, have particular names. We've got the alkali metals, the alkaline earth metals, the transition metals. These here that are highlighted are the halogens. That's right. And in the last row, last column, last group, those are all the noble gases. On the bottom of the periodic table, we also have the lanthanides, because they start with lanthanum, number 57, and the actinides, starting with actinum, number 89 on the table. The periodic table isn't always this easy, but this is how we can have some great fun in chemistry. Atoms are the basic unit of an element that can enter into a chemical combination. The 7 at 7 are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. The polyatomic ones are the phosphorus, arsenic, and sulfur. All can be polyatomic. And those are some unique ones that we won't be using a lot in this course. Each element has one more proton than the element before it. So as you keep adding the protons, you go along the table. The protons and neutrons account for most of the mass of an atom. A proton actually has about 1,800 times the mass of an electron, and a neutron is almost equivalent, but not quite equivalent. Almost equivalent to a proton. It's actually a little bit more massive, about 1/1800th more massive. Now you can estimate the number of neutrons in an atom by subtracting the number of protons from the average atomic mass of the element. So, the atomic mass of an atom is determined by summing the number of protons and neutrons. It's not identical to the average atomic mass of the element given in the periodic table. If you change the number of protons in an atom, you also change the elemental identity of that atom. So each element has one more proton than the element preceding it. The atomic number of an element is the same as the number of protons. And if it's neutral, it's the same as the number of electrons as well. The mass of a proton is titled as 1 AMU, that's atomic mass unit, and the mass of an electron is so small, 1/1800th, that it's rounded down to 0. So an atom is measured in atomic mass units, is simply the sum of the protons plus the neutrons. So let's see if we can check in and use our periodic table to identify these elements. Now let's see if we have our answers. Atomic number 18, so we look up at our periodic table. Atomic number 18 is, see if I can get this to work, there we go. Argon has 3 electrons when the atoms are neutral. So it's got 3 electrons, it's going to have 3 protons. 3 electrons, 3 protons, that is lithium. And atomic mass 16. Again, this is rounded to the 10th place. This is oxygen. In learning about elements, we also have to learn about a type of element, a type of combination called an isotope. So, if you have a chemist that investigates a sample of lithium, found that some lithium atoms have a lower mass than other lithium atoms, even though they're both lithium. Here are some pictures of these 2 elements. So if you look at these 2 atomic pictures, what is different about these 2 atoms? What is the atomic number of each atom, and what is the atomic mass of each atom? From the slide you can see here, as you pause to do this, different about the atoms. Okay, you can definitely see that there's something different about the atoms, and it involves this area of the atom here. This area here called the nucleus. Now in this case over here, this picture, we have 6 total pieces. 1, 2, 3, 4, 5, 6. 6 total pieces. In this one we've got 1, 2, 3, 4, 5, 6, 7 total pieces. Okay? Now both of them are lithium. If they both are lithium, there's something different about them. They both have 3 electrons. So if we get our protons, electrons, and neutrons, there's 3 on this side, there's 3 on that side. Protons, if they have 3 electrons, they're lithium, they're neutral, they've got to have 3 protons. So, something accounts for the difference. This has a mass of 7 AMUs, the one on the left has a mass of 6 AMUs. So looking at the difference in mass, it must be due to the neutrons. So on the right side we've got 4 neutrons, on the left side we've got 3 neutrons, and this accounts for the difference in mass. The atomic number of each atom is 3, the atomic mass of each atom, we've got on the left side it's 6, on the right side it's 7. This here is known as lithium-7. This here is known as lithium-6. These two are what we call isotopes of lithium. So both of these atoms are the same, but they are different because they have different number of neutrons. They're called an isotope. So looking at what we're going to cover, we're going to talk about the average atomic mass, we're going to talk about isotopes, and determine number of protons, neutrons, and electrons. Atoms of the same element that have different numbers of neutrons we know are called isotopes. Symbols associated with isotopes, here is the mass number. This is referred to as boron 10 because it's got 10 neutrons and protons, and then boron 11 neutrons and protons. Okay? Make sure you use the number for the mass number, not the number of neutrons. This boron here happens to have 6 neutrons. This one happens to have 5 neutrons. We do not call it boron 5 and boron 11 because it's the mass number that determines the identity of the isotope. So isotopic symbol and name. You have the mass number, the atomic number, and the chemical symbol, like we've seen. Mass number equals the number of protons plus the number of neutrons. And the chemical symbol or name, you take that and you minus the mass number from it. You put a line in the mass number, so this would be how to show its symbol. So if you had carbon 12, it'd be carbon-12. That's another way of writing it if you don't write out the whole name, or carbon-12. So if you look here, this first one here, it's got 1 proton in it and 1 electron. So if it's got 1 proton, what element is it? That's right, it's hydrogen. This one here, 1 proton, 1 neutron. It's hydrogen, but it's got an extra neutron. And same here, these are all hydrogen, but this one has 2 neutrons. So this is 1,1H. This one, it says hydrogen 1. What's the next one going to be? That's right, 2,1H. And then 3,1H, of course, hydrogen 3. These hydrogens, different isotopes, have common names. First one called hydrogen, or protium. Second one, deuterium. And third one is tritium. Here's 2 other isotopes, one of sodium and one of silver. Sodium 23 and silver 109, that's right. Sodium 23, you'll see here, is easily cut by a knife. You see the shiny material as elemental sodium. And silver 109 looks like that. Now, the special notation is used to symbolize an isotope. One way to refer to isotopes is to use their mass numbers. So let's see if we can calculate the atomic mass of neon. So if you look at this picture, calculate what would be the atomic mass of neon using this picture. So we've got 3 types of neons. Take a moment to do that. We've got neon 20, neon 21, and neon 22. So neon 20 is the blue one. There's 100 atoms total in the picture, 100 atoms of neon. So I'm not going to do the blue one first to count. But how many red ones are there? Oh, there's only 1. So there's 1 of these. Okay, that's going to be 1%. Okay, 22, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. Again, that's 9% because there's 100. 9 per 100. And the last one, there's 20. Well, that has to be the rest, so that's going to be 90 per 100. So what you do is you just take the atomic mass, as you know, 20 times 90 over 100, or 90% of 20, and that's going to be equal to, we pull out our calculator, or do it in our head, because some of you know what it is already. That's going to be 18. 21 times 1%. That's going to be 0.21, 0.21. And then 22 times 9 divided by 100. That's going to be 1.98. If you add up all of these masses here together, 1.98 plus 0.21 plus 18, this gives us an answer of the atomic mass of neon is 20.19 AMU. So that's how to determine the average atomic mass given a picture. If you're not given a picture, most of the time you're given the percent abundances. So you'd be given the 90%, the 1%, and the 9% in this case. So let's look at a problem where you have these percentages. You've got 98% oxygen 16, 1.5% oxygen 15, and 5.5% oxygen 18. It's asking what would be the average atomic mass. So we've got three different isotopes here. We'll list them out. We've got oxygen 15, oxygen, let's see if we can change this to a white color so you can see better, oxygen 16, and oxygen 18. So we write down the percent abundances. So the oxygen 15 I did first is 1.5%. Oxygen 16 is 98%. And oxygen 18 is 0.5%. Okay. Now when we multiply by a percent, it's per 100, so 15 times 1.5 divided by 100 is 0.225. That's its partial mass, and again this is in AMUs, unit for atomic mass units. 98%, 98 times 16 divided by 100, that equals 15.68. So this is 15.68 AMUs. And the last one is our 18 times 0.5 divided by 100. 7.8409 divided by 100. Sure we get this right. This one usually people make the mistake. They forget to divide by 100 because it's already a decimal. 0.5, it's a decimal of a percent, so you got to divide by 100. So here's our 0.0788409 AMU. So how you choose to do that, I like doing percentages divided by 100 when I do percent abundance so I don't forget about it. You take the isotope mass, whatever that might be. Sometimes it's a whole number, sometimes it's actually a decimal. You can still do that. Multiply it here, that equals the partial mass, and then you add up all the partial masses here at the end. 15.68 plus 0.078, so on, plus 0.225, and this equals a mass of 15.98 AMU. You'll notice I rounded to the hundredths place. Okay, we're probably going to do that on most of our average atomic mass. So when you add all of these up here, you'll notice when you add these up, all of these up, there we go, the percent abundances should add up to 100%. Okay, these when they add up, they give you a total mass if all of these isotopes were there. And the percentage is for the average atomic mass of the substance. It's 100% of its abundance equal to 15.98 AMU. And that is your answer. So here's the problem here. Rounded a little bit to the 0.09. Let me see if I made a mistake here. 0.5 times 18 divided by, oh, yep. Right, for that number, but there's the 0.09. So the number, if you got a different number here, let's correct this here. Let's correct that there. So that is definitely wrong here. I don't know where I got that number from. Sometimes that happens. So you just want to double check your numbers. It's a little bit off. So this was 9 divided by 100, which equals 0.09. And you add that to 15.68 plus 0.225, and we should get an answer of 15.995 AMU. Just like a normal average atomic mass problem, you gotta watch what you're doing and be careful with your calculation. So this is what not to do when you make a mistake. But you always want to go back and check it. So that's how you get the 15.995 AMU for the average atomic mass. Now, this is the weighted average, and it's important to understand the weighted average. Weighted averages are similar to how your grades are determined. So your grades are determined by a similar method. Okay? In your grades, your unit tests are a larger percentage, so they're worth more. So you want to do well on a unit test, which means doing your work, doing all of the problems and lessons we do. So, same type of format. The most common isotope of an element is frequently has the mass that is close to the average atomic mass given in the periodic table. So if you look on the periodic table, there's usually a decimal number, and the most common one is going to be the average. It's going to be closest to the average. So if we have an element like boron, for example, it's got an average atomic mass of about 10.81. Okay? You round that to 11, and boron 11 is the most common isotope of boron. However, if you round down, which again, you don't want to round it down for the most common, but the other most probable one would be boron 10. And there could be other isotopes. This is just the most common two isotopes of boron. So there could be 2, there could be 3, there could be 5, there could be 10, there could be even more naturally occurring isotopes. Now, atoms of the same element can be different by a different number of neutrons. Same elemental properties, same physical properties, they just have different masses. Isotopes are referred to by their mass numbers, such as carbon-12, and to get that, we use the weighted average. So here's a check-in question for you to do. Good luck. To wrap up what we know, property of a particle that determines electrostatic behavior that's central to chemistry is called charge. Number of protons, when it's less than the number of electrons, you have a negative charge. When the charge number is equal to the number of protons minus the number of electrons. So depending on if you have more protons or more electrons. This determines what's called the charge number. So we looked at changing the number of neutrons, now we're looking at changing the number of electrons in a particular atom. And then it becomes a charged particle. You want to write this as the magnitude and then the sign, so whether it's positive and negative. The amount and then whether it's positive or negative. So 2 plus, for example. More on charge. If you look here at our XAZ format, the C here you'll notice here stands for charge. You got the mass number, the atomic number, and the charge number. Charge number is number of protons minus number of electrons. So, how would we write the isotopic symbol for an atom with 78 protons, 119 neutrons, and 75 electrons? Please do that now on your paper. And let's check and see how we did. Monkey scratching your head. Hopefully you're not scratching your head. Pause the video. Here we go. 5, 4, 3, 2, 1. And the answer is platinum 197 with a 3 plus charge. 78 is the atomic number because it is platinum. This is called an ion. An ion is an atom that has a net positive or negative charge. Ca2 plus, Ca plus 2. Okay, charge is written with the number first, then the positive or negative. Na1 plus or Na plus also works. Calcium, to write it properly, would be calcium 2 plus or calcium with 2 positive signs. That's also one way of showing the charge. Polyatomic ions are when you have a group of atoms chemically bonded together that has a net positive or net negative charge. So it's a group of atoms that come together that as a group have a negative charge or a positive charge. We've seen a couple of these in the laboratory, like the hydroxide ion. this has a negative charge. The nitrate ion, this has a negative charge. The sulfate ion, this has a negative charge. Okay. Most polyatomic ions happen to be negatively charged. There are some that are not, and we'll look in more detail at how a polyatomic ion works. But it acts just like a regular ion, but it has more atoms in that one ion, and they function together as a charged particle, even though they might have more than one atom in it. So here are two other ones. Ammonium is a positively charged polyatomic ion, and this other one, PO4 negative, 3 negative, that's called phosphate. Cation are the positively charged ones, and anion are how you remember the negatively charged ones. How I remember cation is if I look here, there's a positive sign right in the word cation, that's a positive sign. And then anion, here, the word anion has an N, first N, that stands for negative. Just an easy way of remembering it for me. That's the end of the show for tonight. We'll see you tomorrow.